This information is brought to you by Charles Sturt University.
What we were talking about last lecture was looking at probability distributions, which pretty much is looking at a number or some sort of category of all the different options you want to consider, and you have a probability assigned to each of them.
I just feel like doing that.
Missed that.
I was talking to Corey.
And so we want to be able to utilise these distributions and do some calculations on them. But one sort of key idea is to, given a distribution, is to be able to describe it. So looking at the shape, the centre and spread. So what we looked at last lecture was the first two of those. I just want to do them slightly again. So just recapping some of the things we did. So we looked at two key examples, which are up here. I want to talk a bit more about them. So we looked at, if you toss a coin 3 different times, how many heads do you get?
It's 15, isn't it? 15.
So you can either get 0, 1, 2 or 3 heads. Essentially the 3 different options you can consider. There's lots of numbers up here, but so they're the 3 number of heads you might get from tossing a coin 3 times. And the key thing we want to know really is the probability that each of them happens. So what's the probability of getting no heads? And it ends up being 1/8. Probability of 1 head is 3/8. And we did the calculations for it last week. So that's the probability distribution essentially. Just really the possible values it has and the corresponding probabilities. That's really what it corresponds to. And we want to try to understand that. So you can do graph. So this is the theoretical distribution for it. So just a picture of those 8 different numbers essentially. So it's plotting the different x values you have, the different values, the number of heads on the x-axis, and the height is the probability each of them corresponds to. And that would be symmetric, is how we described it last week. So what we want to do is do other things, like talk about the centre and the spread of these distributions. And the way you've done centre previously is looking at the average. So I want to do the same thing again here. So I mentioned the formula just at the very end of the last lecture. Just want to give it a sense of where it might come from. So what you can do using Excel here is I can just generate a bunch of 100 different random numbers here corresponding to this tossing the coin 3 times. So especially if I just press F9, it regenerates all the numbers for me. So this is the graph of if you toss a coin, if you toss 3 coins 100 times, and at each time you work out how many different heads there are, this is the sort of graph that corresponds to it. So I just press F9 a few times, you can see it changing. Does it match the theoretical picture over here?
Hell no.
They're not exactly the same. It's only 100. The theoretical responds to if you did it an infinite number of times, I guess you want to put it that way. But if you keep doing it, sometimes it looks pretty close, sometimes not as close. But if I took a sample of not 100 but 1,000, then the picture would look better. Like it's because it's only a sample of 100, you get more variability. If you made it a bigger sample, you wouldn't notice the difference so much. So you can see that by taking a sample, you do get a reflection of what the real one's like. But it does help with some other ideas. So how would you work out the average of these 100 numbers? Simple question.
Go back to basic maths, add them all up and divide by how
Okay, so add them up, divide by how many there are. That's right. So we're looking at average. So just mucking around for the moment. So essentially, when you look at all the numbers, they're all just 0, 1, 2 or 3. That's the only options you want to get. So essentially, if you want to add them all up, while you look about, again, you might remember this as frequency, how often each of them crop up. So let's just, here they are here. So this is for the, so just do a bunch of random numbers. So that's the corresponding frequency. Let's just copy these down. So 12, 38, 40, and 10. So they're the frequencies for one particular random sample. So we have 12 zeros, 38 ones, etc. And so essentially what you do is you could add up 12, just do 0, 12 times, add them all up. Doesn't sound like very fun. So a quicker way of doing it, just adding up all the numbers essentially, would be to say that, well, these 12 zeros contribute, well, there's 12 of them, each has 0 value. So 12 times 0 is how much that will contribute to the sum, which is nothing, as you can imagine. The ones, there's 38 of them, each would contribute one of them, so 38 times by 1 would be how much that contributes to the sum. And same thing for the 42s and the 10 3s. That's how much each of those contributes to the sum. So you just add up these numbers now. So 38 plus 80 plus 30 gives you 148, I think it is. Does that make sense? So that's really just adding them all up. What do you do next? You just said before. Once you've added all the numbers, what do you do with them?
Divide by 100.
Okay, divide by. So then we want to divide by how many there are. Divide by 100. So the average would be 1.48 in this case.
So I'm just wondering though, because your frequencies only add up to 90.
No, so that's...
Out to 100. Do they? Yeah. Oh yeah, they do, sorry.
Yep. I hope they do.
Yeah.
So that's the average. So the average in this, and that's just the sample. That's just the sample of these 100 numbers. And again, that really is just adding up numbers divided by total. That's how you're normally used to it. So what we want to do is carry that idea that we can do it for these 100 numbers. We want to apply it to a whole probability distribution, essentially. So just sort of think, how does that sort of carry through? So if you think of basically what we're doing here, essentially we're multiplying the number by how often it happens. Sorry, just rubbed the wrong, he's out. So pretty much we do it 0, we multiply by how often it happens, so 12 in this particular case, and then divide it by the grand total. So effectively multiplying 0 by 12 over 100, and 1 by 38 over 100, 2 by 40 out of 100, and 3 by 10 out of 100. If you then add up all those numbers, you would still get that 1.48 again.
Whew, that's an interesting looking one. 3 times 10 over 100.
Okay. Thanks. So you could essentially, instead of multiplying by the frequency, you can and then dividing by 100 at the very end, you can multiply by what's called the relative frequencies. Same sort of deal. So if that's just for 100, this is just for a random sample, but if you make it bigger and bigger, these numbers here would end up being the actual probabilities. The actual probabilities various things happen. So this is the sample. So in theory, so if you did the whole thing many times, so if you did it for the whole distribution essentially, then instead of multiplying the number by the relative frequency of the sample, you'd multiply it by the probability that you get that thing happening. And 1 times by the probability that would happen for 1, etc. And then you add up all those different numbers to get some sort of average. So what that boils down to is that the average of a whole probability distribution then really just amounts to working out all the different values you can consider, all the different x values, work out the probability that corresponds to that, multiply them, and then just add them all up. And although it doesn't look like averages like you've done before at first glance, it really is the same sort of idea. It really is adding up all the values, dividing by how many there are. It's just that instead of doing that directly, we're just using relative frequencies to help us out. So essentially dividing weights by how many things there are straight away. So that's how you, and that's what the average is. That's how we're going to work at average. So, for example, for the heads example here, we've got 0, 1, 2, 3. The probability was 1/8, 3/8, 3/8 and 1/8. That's what the probabilities were. If you wanted to work out what the average of these things is using that formula, we first work out what x times by the probability actually is. So what's 0 times by 1/8? 0. What's 1 times by 3/8? 3/8, yep. 2 times by 3/8?
6/8.
Yep. And the last one, 3 times by 1/8?
3/8.
So if you add up all those numbers, just add them up, what do you get?
Yeah.
12/8. And you're just going to write that as a decimal effectively. So that's going to be
1.5.
Yep. 1.5. 1.5 as you said. So that's how you work out the average of a probability distribution. Really work out, you need to have the table effectively written down for you, as I'll often give it to you. And then once you get the table, just work out x times by the corresponding probability, then add up all those different numbers. That gives you the average. Interestingly, that's the theoretical one. What do we get for our sample? Is it close? Yeah. So for a sample, you can see that the average of a sample is close to the average of the population, is the fancy word for it. So if I did, that's the average of the sample, that's the 1.4 right there. So if I just keep pressing it, you can see average changes every time. Sometimes it's too small, sometimes it's pretty close, sometimes it's too big, etc. But it does change what the sample is. But if you make the sample bigger and bigger, it varies less and less, essentially. There's more stats for that, but it does give you a sense of how things work out, because you're more used to taking average of just a few numbers, effectively. So that's looking at the centre, how to work out what the centre is. But we want to do more than that. We want to give a sense of how spread out things are. The other example we did was, apart from tossing a coin 3 different times, the other one we did was looking at sorry, you can see it all. Looking at if you're getting a bag which had, I think, 3 red balls and 5 red balls, and picking 5 black balls, even, thank you, and picking 3 of them from the bag. What distribution do you get? And we worked it out last week. All the various probabilities out for them are. That's the distribution. So you can change it around. So let's make it 5 red and 5 black, for example, just for contrast. So if you've got 5 black and 5 red, and you want to pick 3 of them from the bag, that's the corresponding distribution. So it looks nice and symmetric because there's an equal number of red and black balls, essentially. What do you reckon the average of that distribution is going to be? So the average really is a measure of the centre. What do you reckon the centre of that picture is? Essentially is what my question's asking. What's the central value?
1.5.
Yeah. So if you look at it, it's pretty symmetric. So the guess is it's going to be right bang in the middle, halfway between the 1 and the 2. So the average isn't going to need 1.5. So for the heads example, the average is also 1.5. Are they the same? Does the picture? So if you look at the probability for the 0 here, it's 1.25. For the red and the black, the probability is less than 0.1. So you can see that the distributions are different to each other. So as a matter of fact, if you did a heads example, you're more likely to get 0 or 3 heads, or if you did this red-black balls from, you're less likely to get those extreme events. So how I've described it is this second case is less spread out than the first, because you're more likely to get just a few values. That's much more common. So when you've got a really strong peak, that's less spread out. When you've got a really low peak, so everything's all over the place, that's more spread out. And so looking at shape, so both of them symmetric, and looking at centre, so both of the centre 1.5, is not enough to distinguish between the two, so we need other ways of describing it. And the next simple thing is to talk about the standard deviation or the variance of the graph as a way of measuring this how much spread out it is. And so looking at these two just give you an idea of why we need to look at that as something extra. So you guys remember how to do standard deviation or variance from school? Anybody? So you may have just used your calculator. Got a calculator to do it all. So I'll have to explain the formula a bit. So, as a matter of fact, it's actually, if you're going to do it by hand, and we are, it's actually easier to work out the variance. So the variance is a measure of spread. So I'll tell you what that is in a second. The one that you're more likely to have heard is the standard deviation. So the standard deviation is the square root of the variance. So before I go any further, does anyone heard of these terms before? Who's heard of standard deviation before? So maybe half. So more than half class. So that's the one you've heard of. There's actually a button in your calculator to work it out for a sample. We're talking about different stuff here. But the way we calculate it, and then how your calculator works it out when it has to, it first works out the variance, then when it has the variance, it takes the square root to work out the standard deviation. So the one we're going to deal with more directly is this variance. So, give a bit more of a bit more information.
Very good.
So the way we write down these things is the variance is basically the expected value of the different random variable minus the... Okay, I think I need to just put a few more things down. So let's give a bit more notation just to help explain what I'm about to write down. Can you put your phones away, guys? Not helpful.
Just assignment just got marked.
You can wait till
the bad spelling of the...
Yeah, so I write down EX for the expected value of a variable, random variable, X. So the E stands for expected value. So that's what I expect on average to be. And really, we think of that in all common language, we just call that the average. That's what I will write the average down as. So the average is just the expected value of X. And the way we work it out, as I said before, is just summing over the value, X, times by the probability of getting that, all over the different X values. Just summing it all. So that's what I mean by expected value, just summing over all the different values. So we can work out the expected value for an actual variable, but we can work out other things too. So we could work out what the value we expect for X squared, with 1 and 2 for example. We could also work that out. So that's, and what does that correspond to? That would be the average value of X squared, which at first glance you go, what does that mean? I'll get there. I'm about to use it in a second. How you work it out, which is the more important thing for the moment, is you work out the corresponding X squared value, multiply it by the corresponding probability of getting that particular X value. So before going further, let's just see what that looks like in this previous example. So previously we worked out the expected value for the x value itself, the average, 1.5. We can do the same thing for anything else. So we can do the same thing for x squared, for example. And the reason why I'm doing this is because it helps with the variance, but in a second. So I've just got to, I'm getting there. So what you need to do then is you need to work out what the squared value is. So 0 squared 0. Multiply that by the corresponding probability of getting that x value. And we'll do this for every single value. So 0 squared times 1/8 is 0. That's the easy one. Next one is 1 squared times 3/8. Next one will be 2 squared times 3/8.
Yeah, 12/8.
12/8. And this one is 3 squared times by 1/8.
That would be 1. Wait, what? That's 1/9. Oh.
Sorry, I didn't write it down properly. 9/8. And then we can add these up. So you got 3 plus 9 is 12, plus another 12 is 24, over 8 gives you 3.
Oh, that's 1.5 squared. It's 1.5 times 2, okay.
Now, and it's important to notice that's not the same as 1.5 squared. So it's the expected value all squared is usually not the same as adding up as the expected value for x squared. They're often different numbers, as you can see in this case. If they are indeed equal, it means that the values are the same all the time. It means it's that means only one value is ever possible at 100%. It's any time it's ever equal. So that's how you work out what ex squared is. So that's the expected value we'll get for x squared. So we can do it for other sorts of things too. So the variance, there's two sort of formulas for it. We can either work out the average first, that's EX, and then work out the expected value of x minus that average, all squared. That's one way of working at the variance. That's sort of the formula. I'll talk about what that means in a second. Well, let's do the calculation formula. So how you actually calculate it in practice is you'd work out EX squared, like I just showed you a second ago, and then you subtract off the average all squared. That's how you work it out in practice. So the first one is the meaningful formula. It tells you what it's really trying to do. The second one, it tells you how to calculate it. So let's calculate it, and I'll talk about what that means. So EX squared we worked out just a second ago, so this is the heads example, was 3, and the expected value was 1.5, and then squaring it would be EX squared. So what's 1.5 squared?
2.25.
Yep. So 2.25, and take the difference of those two, gives you 0.75. So the variance for the heads example is 0.75. So, and then what we can do, if you want to do anything with it, you want to do things like standard deviation. So the standard deviation would be the square root of that, which is 0.8. I can't remember the rest of it. So that's all I can do. So it's root 3 and 2, but someone can tell me better than that. It's a non-terminating decimal, so maybe 0.8 would be my really rough guess. As you're about to look it up and work out what the real answer is, what does this all correspond to? So a bigger picture, the variance and indeed the standard deviation is a way of trying to estimate how spread out something is. And although this is in terms of vector values, this all really corresponds to how you work it out for a sample as well, just generalises that. This formula at the top here sort of tells you what it's trying to do. Let's just give a sense what it all breaks down to be. So the EX really is the average value. That's what the average value is. So therefore, X minus EX then is how far away it is from the average value. Just tells you how. So X was 0, 1, 0, 1, 2 or 3. They're the 4 different values we have for X. So a value of 0 is 1.5 below the average. An X value of 1 would be minus half below the average. So this expression here is the deviation from the average. So it just tells you if it's above or below, so it can be plus or minus, sort of tells you how much the deviation is. So what I want to do is I want to get a sense of how spread out it is. So if it wasn't very spread out, most things would have the deviations being pretty small. Or on average, the deviations would be small. There wouldn't be very big deviations. That's what you expect for something not much variability. So our first thing is, why don't I just average it? Why don't I just take an average of these deviations? The problem is if you do that, some deviations are negative, some are positive. If you add them all up, they cancel out to give you 0, which doesn't really work very well. So what we need to do is we need to make these deviations positive before taking the average. And so one idea would be, let's just take the absolute value, if you know what I mean by that. That makes them all positives. The problem is the formulas get really nasty. And so after exploring different options, people worked out a long time ago that the most easiest way to make this positive would be just to square the deviations. That makes them positive. Now it comes with a cost, which I'll mention in a second, but essentially that's what we're trying to do. So the deviations is how spread out it is, squaring it to make them positive, and we just want to work out what the expected value of that, and that's really what the variance corresponds to. Now the downside of that approach is if all the original numbers, so if you had units for all the numbers, so they're all meters or something like that, then the variance would then have units of meters squared. So it sort of stuffs up the dimension. So in order to get the dimensions back right again, you need to take a square root at the very end of it to get everything making sense. So therefore, the more common way of talking about these things is that standard deviation, which has that square root in it, just to get rid of the square root introduced in the first place. Now, it might seem, that seems a really bizarre way of doing it, but mathematically, so in terms of things like calculus, which you've seen at the end of Maths 105, most of you, it's much easier to take a derivative of x squared than it is the absolute value of x. And therefore working out result coming around to that is much easier to have this quadratic sort of equation. Now, most of that won't mean anything to you perhaps, but there is reasons for it that people have thought through. So let's just recap what I said here. So the average, which I write down as EX, and sometimes just to write a different letter down, sometimes I write down mu for that. Mu. That's the Greek letter for M.
Pretty rare as well.
And why M? M for mean is where the letter comes from. And the formula for it is just basically adding up the different x values times by the probability of getting it. That's the average. If we do any calculations, we would work out what EX squared is, which is summing over x squared times p, x squared times the various probability of it happening, and then the variance. So the calculation form for the variance would be working out this EX squared bit and then subtracting off the average squared. That's pretty much the calculation formula, and you work it out in practice. And then the standard deviation, if you never needed it, would be the square root of the variance. So it's sort of summary of what I've been talking about. So what we did, we've worked out the average, variance and standard deviation for the heads exam, essentially. And we worked out, So let's just compare them. So for the heads example, the average was 1.5, and the variance, can you see that? It's 0.75. So let's look at the red and black just to show you some things different. So this is the red and black example where they're picking 3 balls from a bag containing 5 red and 5 black. So again, it's a symmetric distribution. The average is still 1.5. If we compare the average, it's still 1.5. The computer Excel here can work out the average. It's not 0.75 anymore. It's 0.583. So the variance is decreased. If you work at standard deviation, that's correspondingly smaller too. So that tells you that this example is less spread out or more compact than the other example. Do look at the pictures. That means you're more likely to get 1 and 2s than compared to the coin tossing example. That's what it's trying to measure. Now, the best way of just understanding standard deviation is in terms of norm probability, which I'm not going to mention. But
easiest way to understand it is something that you don't need to know.
Yeah. Unfortunately, that's incredibly true.
That's really insightful.
So I could mention it, but it just confused you more to begin with. So the standard deviation for the moment, it really is. So there is good basis for it all, but the main reason we're going to use it is just to compare stuff. So we can compare. So it's some way of measuring spread. For the moment, it seems a bit arbitrary. Well, I'll just square it. What does that ever correspond? What can I point to in the graph? The answer is not really. Not the way we do it. But you can use it to compare. So just like I've worked at standard deviation for 2 different distributions, you can compare them directly. So it's just some number generated. There's a rationale for it that's just hard to explain it from where I am, without explaining a lot more. But you can compare it. So it's a really nice thing. You go, well, this deviation here is much bigger than this example. That one's more spread out. So you can measure it that way quite clearly. And so really just thinking of it as a way of measuring how spread out it is. And the opposite of high variability is lots more compact. So that's just trying to look through looking at expected value and variance and standard deviation of a probability distribution. So the other things that are useful to do in various contexts is to look at, you want to sort of compare distributions sometimes, and so looking at the averages and the standard deviations are useful ways of doing it. But sometimes you want to compare things right side by side. And if they have different means and different standard deviations, it's hard to compare them side by side. Like that last one was easy because they have the same X values, etc. So one way of approaching it is to look at what's called the standard score, or the Z score. Has anyone heard of Z scores before? So 1.5 people. So it depends what you did at school. Sometimes some levels at school in New South Wales mention it, and some don't. So I mean, the fact I've never even seen it before is very popular. So it's not that hard to work out. So to work out a Z score, basically you get the corresponding value. So in this case, 0, 1, 2, or 3. Subtract off the mean, which we worked out. That's the 1.5 for the heads example, and divide by the bottom here is called the standard deviation. So just write it down. So the Z score is X minus the average over the standard deviation. And so this is, so what it corresponds to, I mean, this is the number of standard deviations away from the mean. That's what it corresponds to. So it's basically how many standard deviations away from the mean. So things with a very high value for Z, either really positive or really negative, suggest they're very far away from the mean value. Things which have a Z value close to 0 are very close to the average. And it's all in comparison to how much better long variability is. So it's a way of measuring how close things are or far away they are from the mean based on the actual spread of the data. So let's do some calculations and I'll talk a bit more about some rules of thumb with them. So for the head, this is the heads example. So we had 0, 1, 2, 3 various probabilities. So the average value, 1 to 1.5. The standard deviation was 3 and 2. It is 0.866 would be the standard in this case. So the Z values would be, or the Z scores, or the standardised scores, is the value you have, so 0, minus its average value, minus 1.5, divided by its standard deviation, at 0.866. That would be the Z score in this case. So I'm telling you on the calculator what that corresponds to.
Minus 1.732.
Minus 1.732. So let's do the next one. Next one would be the value. So it's 1 minus the average divided by the standard deviation. So again, it's another negative number. The answer is
Negative 0.577.
next one will be 2 minus 1.5 over 0.866, and this would be the positive of that last case, and the last one would be 3 minus 1.5 over the standard deviation, which would be the positive of the first case. In this case, I mean, because it's symmetric, it's easier to do the second half. If it wasn't symmetric, you wouldn't get. You have to actually work them all out. So that's the Z scores. So these are what's called the Z scores or standardised scores. So the probability of these things happening. So there's a nice link between probabilities and what some of these Z scores are likely to be. So Z scores beyond plus or minus 2 don't happen very often. So as you can see here, there's no Z score plus or minus 2, they're not that extreme. So roughly speaking, you only get values bigger than 2 about 2.5% of the time on average. That's sort of the rough guide. And even less than minus 2 about another 2.5% of the time. So that don't happen very commonly. So the Z scores also give a sense of some sort of sense of likelihood as well. And then you have probabilities, we have them written down as well, so we actually have those at our disposal, but you can often see nice links between them all. But that's often the way when you've got two quite distributions, you have quite different X values at the first glance, different averages, different standard deviations. These are one way of comparing them on the same page, so to speak, by putting them all on the same scale. So essentially, I mean, if you had a bunch of, so another way, you have probability distributions not for the number of heads or balls, etc., but it could be for the number of metres or how tall someone is or anything like that. So how high someone is when they rob KFC, you have that sort of distribution if you wanted to. And so if you measure in centimetres or metres, you get quite different values. If you measure in centimetres and feet, you get quite different values. Now they're easy to compare, make them the same, but if you measure it to the nearest 10 centimetres or the nearest foot, you also get different values. So by looking at Z scores, it really just makes them all on the same level. It really just brings all the scales to the same area. That's sort of the benefit for them. And so, that's some of the reasons for it. So there's other good reasons for it. So that if you've got a big enough distribution, being vague or big enough, then these z-scores are commonly what's called a normal distribution, which is a terrible name. So Gaussian distribution is less common, but also another name for it. So that's more. There's more on that. That is not discrete maths anymore. That's called continuous mathematics, which is what I'm doing the subject. But there's a link between what we're doing here and lots of that sort of stuff. So that's just a bit of a recap for some of these things you can do with distributions. So we'll do a few more in a second. So before doing that, I just want to digress to look at some special probability distributions. So sometimes you get distributions cropping up in a simple case. So you actually manufacture it. So say, for example, you might be designing a game, something like that, you just might make it up. You might go, look, I just want to make a different distribution up and make the probabilities up myself to get some sort of pattern happening. I'll work out the average and standard deviation just to see what sort of values I might expect. You might want to do that yourself. Other times distributions crop up from a particular situation. And so I want to look at two in particular. And once you have this particular situation, there's a neat formula to work out all the probabilities. So the first case is called a binomial. We've actually already seen this one. So the tossing the coin 3 times is an example of a binomial distribution. That's one of the special cases. So how it works is if you do the same thing n times. So for the coin, you're tossing it 3 times, the same thing 3 times. Each time, the outcome is independent of all the other. So when you're tossing your coin 3 times, we're assuming that if you get a head or a tail the first time, it doesn't change if the next one's a head or a tail. That's what I mean by independent again. So each of them are independent. And the probability, and there's really going to be 2 outcomes, either a success or a fail. So for coins it's easy, just head and tail. So some sort of success or fail, and it's not moral, so it's not as if success really means good. So sometimes success in these cases means the mouse dies. So success is a really bad word often. So it's just a way of labelling 2 options, really. So one option versus the other option. And we assume that the probability is the same every single time. So for tossing a coin, we'll always assume we've got a 50% chance of getting a head, for example. Then if you want to count the number of successes, in quotation marks, then that has a binomial distribution, well-known formula, etc. So why is it called binomial? So the bi means 2, the nominal bit means name, so really this thing's something called 2 names. And the 2 names would be the success, failure, or heads, tails, as we've seen previously. So, an example other than the coins example.
Or mice.
For mice, so...
Ebola. I do think Ebola is that.
So, 10 mice get subjected to a virus. There's a 1 in 4 chance, or 0.25, 25% chance the mouse will die.
Ebola. Zika virus.
Then you can work out a variable, the number of mice that die from the 10. What are the possible values that X can be?
Just A and B. Talking about.
There's 2 options, die and not die.
So that's each mouse has 2 options. What about X? X is the total number of mice from 10 that die. So X is a number.
0 to 10.
2.5, total number of mice that die.
That's the average value. What are possible values can X be? Can be lots of different values. 0, 1,
2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, so everything from all integers from 0 to 10. That's right. So that's all the different values. And what we could do
that scientist wasn't a mouse.
is we could work out the probability for every single one of them. So we could work out probability for having none, or probability for 1, or probability for 2, etc. I'll show you what the formula is in a second. So the first thing is, before we get to that stage, is you want to just be able to use the formula, but you need to recognise it's binomial. So how you recognise it's binomial when you have 2 distinct options. So you got a bunch of repeated trials. For each trial there's 2 very clear options. That's what binomial. That's the biggest giveaway for it. There's 2 things you need to know, and normally that gives the question away. One is how many trials you're doing. That's N. and the probability of a success for individual trial. So in this case, we're got 10 mice, so there's 10 different things we're looking at. So N is 10. Each mouse has a 25% chance of dying, so that if we're going to count deaths, then the probability of that happening for an individual mouse is 25%. So that's what P is. And you need to know what N and P is to use any of these formulas. So when looking at an example, you need to go, oh, that's binomial because there's two options. They're the same every single time. And then you just need to work out N and P is. And that's normally just reading from a question point. So once you know, once you realise it's binomial, the formula to work out binomial probabilities is given by that one there.
That looks like death wrapped in more death.
There is one number in that formula.
A little bit more death inside.
So, well, see, who's seen that formula before? So if you did extension maths at school, you do binomial probabilities.
Screw that.
If you haven't done extension maths, you haven't seen it yet. I mean, that's pretty much what it boils down to. What does the NCXB mean again?
That's choose.
Okay, that's the choose. That's a button in your calculator. If you really get stuck, it's just your calculator can do that. The rest of it, it's just using powers in your calculator. Key mistakes people can make when utilising it is with this power n minus x, you might have to put that in brackets, or in practice it's probably just either using your head to look at it. I'll show you an example what I mean by that.
What's this one?
No.
Binomial probability formula.
So you do other examples of binomial would be, as I said, tossing a coin heaps of times, or if there's random errors on a disk or something like that, when you're doing 100 accesses to the disk, the number of errors you might get from those 100.
100 faults.
Hopefully not many. That would be examples of binomial, etc.
100 errors.
So let's just do one example to see what the formula actually looks, how it looks like in practice, etc. Now you need to know, you might need to use this formula for your exam, so it's good to have this formula in your cheat sheet.
Write it down.
So you don't have to remember it off the top of your head, you just have to be able to read it.
You just have to remember where the values go.
But that's the thing. Now you need to know how to use it though. It does require practice.
Write a whole essay on your cheat sheet on how to use it.
So x. So it's the same example as before. So x is binomial, and for the distribution, since it's a really generic one, it needs two things, n and p. And we worked out these were 10 and 0.25 a second ago. So that's the same question. So what we want to know is what's the probability that the number of mice that die is 3? That's the question. So what's the probability that 3 mice die? So in terms of our notation, it's probably x equals 3. So let's just put over here the formula, so just copy it down. So the probability that x is equal to some fixed value is n choose this value, p to this value, 1 minus p, the n minus x. Let's just give some interpretation for what it all means. N choose k's, that's the number of ways of picking the x mice that will die from the 10 we have available. Yes. So P is the probability of succeeding, of dying, I should say. Let's just probability of dying to the power of the number of mice that will die. 1 minus P is the probability of not dying, and n minus x is the number of mice that will not die.
Oh my god, subject evaluation. Like he's too morbid. We have like getting on a bus and not getting on a bus instead of just dying and not dying.
Getting on the bus and dying and not getting on the bus and dying.
Oh, I don't know if you like my next example even.
Oh no!
Oh shit!
It's going to be like once you get to the age of 90, you either die or you don't.
So in this case here, we want the probability x equals 3. So what's the n going to be? So just play in the formula. What's the n?
10.
So it's 10, choose 3. probability of success is 0.25 to the power of 3. 1 minus 0.25 to the power of
7.
Now, you could write 10 minus 3. I would encourage you to type that in your calculator as 7, like you just said. If you don't type it in as 7,
It's about 10.
depending on the power on your brand of calculator, you might need to put that in brackets. So therefore, it's going to be much easier to go, oh, that's a 7.
Oh my goodness, this is a lot of stuff.
So I want you to try typing that in and see what answer you get. So it's you need to be able to, as I said, your formula you don't have to remember, but you now have to know how to use it. And so part of that means practicing right now, preferably with a calculator you're going to bring the exam.
Call it again.
Rip Harambe. David, could you please do it? No. Actually, wait, no. I won't even request you.
Do a flip, David. Do a flip. When do you want me to do a flip?
360 no scope, somebody.
One of these tables.
Let's do it.
What's one of these tables? We'll put this in place to get power right now. Well, it'll be best like a power back. No. That's good.
So, using my cheat option of using Excel to get the answer for me, I think the answer is 0.2508. Now, you won't have Excel in your exam.
Yeah.
2508. I got 25028.
Yeah, they look. I like it.
Oh, there you go. I can't even
Haha.
read. Thank you. So, so everyone has had a master their calculator to get that answer out?
Not what I got at all.
David, you
I got
stuffed up.
0.2502. Okay, so you're not very good off your calculator.
So, you need to be able to know. So, the skills you need to know is you know how to use the calculator to do that. Yep.
There's an O in the middle of that, please.
Goddamn right, Jacob.
Yeah.
I was
Thank you.
You can make your notes much prettier than mine. It's okay.
They are, don't worry.
So you need to be able to use the calculator to get that answer out, etc.
Chance of 3 of them dying, 1 in 4.
The 1 4, yeah.
Well, not exactly, David, but anyway.
Well, it's
So
0.25.0282287%, Jacob. Are you happy?
No.
I'm definitely not happy.
I'm never happy, David. You should know this by
You
now.
just said there was 0.25% chance.
No,
He said
25.
25.0.
25.0.
so if x is binomial, then what's this EX mean again?
The
Average.
The average. So the average is n times by p. So in that last case, we had, this is for our mice example.
4 mice will die.
So we had 10 mice. The probability of one dying would be 25%. So we would expect on average 2.5 mice to die. Does that make sense?
2.5.
That's
Back half of a mouse.
That's on average. So it's an average value.
Is it leprosy? Is that what it's got?
That's
Um,
very full on, David.
Well, you know, I'm not the one who made the question.
So the other one is the variabilities. This is the variance of x. The variance of x is n times by p times by 1 minus p.
Oh, okay. All good.
And you can prove it. So you can do a bit of algebra, you can prove these formulas. So in this case, that would be 10 times by 0.25 times by 1 minus 0.25. And that gives you 15/8, isn't it?
Yeah.
15/8.
Whatever that is.
Yeah, it is correct. 875. Whatever you. It's 1.875.
So that's the variability in this case. And so we can work out the standard deviation. How to work the standard deviation of this particular minus example?
It's not 2.875.
No, one.
Yeah. Only 1/8 goes into 15.
Your calculator's not a bad thing. Use it more. So how do you work it? If that's a variance, how do you work out the standard deviation from that? Take the square root of it.
Boom.
And so
1.37.
1.37.
Maths is wonderful. What does that actually mean though? I don't get it all. Does that mean it's like pretty far away from the average? Or like...
So it gives you a measure of spread. So it's really a useful way of comparing two different ideas.
Oh.
Comparing things. So if you choose a different value of p, for example, so if we got p equals 0.25, you had a probability value of, say, 0.5 instead.
Oh my god, that's nice.
So, I mean, there's a 50% chance of dying. What's the variability? Is the standard deviation bigger or smaller in that case? Plug it in. So just do 10 times a half times a half. 2.5. Square root of it, it's bigger than that. So if there's a 50% chance of individual mice dying, actually the standard deviation is bigger. That tells you that there's a much more greater variability in that situation. Whereas if you make the p smaller and smaller, so if you made p equals to be 0.01 or something like that, which means most mice live, very few mice die, there's not much variability there. And the standard deviation would also reflect that by being much smaller. So our main use for it at the moment is just to compare different examples. So what's 1 versus 2 mean? We don't really know, but if we know 1's twice as big though, it means it's twice as variable. That's more what we're using it for.
Okay. I'll buy it.
So here's another example. This is a simplified version of a court case called People versus Collins.
A male Negro wearing a moustache and beard in a yellow car robbed an elderly lady.
Okay, so the real case is a couple was seen doing a bag snatch essentially from a lady.
Oh, it's grammatically wrong, but anyway.
What's grammatically wrong?
Grammatically wrong.
Robbed a elderly lady. Shouldn't it be an elderly
Oh,
lady?
yeah.
It was made in 1968. People were stupid back then.
People are stupid now, David, more so than back then.
When
it comes to grammar.
So the grammar's sake is mine, not the Negroes or the elderly ladies, that's for sure. So a Negro, as you can see, that's description, was seen robbing an elderly lady. Not so far, not just around the corner, a guy called Mr. Collins was picked up, matched the description. He had the right coloured car and look, etc. And they were trying to, he was taken to court, and in court they're having a hard time proving he was guilty, essentially. So they pulled out this special witness who was talking at the probabilities of someone matching all these descriptions. You can shake your heads, that's fine. So they listed the probability of having being a Negro, probably having a yellow car, and all these good things, multiplied them all together, which is wrong in and of itself probably, and they worked out the probability that someone would match all their descriptions was some number. So I haven't used one in the court, I've just done a simplified version of 1 over 50,000. In the area that these people live, there happens to be 50,000 people, incidentally. So therefore, if you multiply those out, there's one person who satisfies that. Mr. Collins satisfies that, so finding guilty.
Yep.
And they did.
Wow.
They convicted him on based on that.
That's
so
pretty
bad.
Sounds right to me.
They
I got
So-
a bone to pick.
they then appealed it, and on appeal, he was acquitted.
Oh.
Why was it appealed? I guess is the question.
Because it's wrong.
It's wrong on a few counts.
It's like, did you see him commit the murder? No, but he's still guilty. What, how come? Well, there was 3 people in the room. The other 2 people, they ran off, but he was the only one left. Therefore, he must have done it.
So this is called circumstantial evidence.
He's the only one who owns a knife in town. He must have killed.
So, but just because all the circumstances might point to them, does not immediately prove someone guilty. That's essentially what it comes down to. So, the jury was confused by the probability that was mentioned at the time, but really it's just all circumstantial evidence. That's all it was. So, just to give you an idea, there's a few flaws in it. The derivation of the probability of 1 in 50,000 was a bit suspect because it basically combined things which were not independent, but they combined them as if they were independent. So when we did probability last week, if you're doing a multiplication rule, you have to use conditional probabilities normally. If you're independent, you can just multiply them quite happily. But if they're not independent, then you can do quite something different. They did not do that. That was one mistake they suddenly made. So that figure is 1 in 50,000, or the one they used in the court, was quite much smaller than it should have been, I reckon. But even if you take that for granted, let's look at the area of 50,000 people. If there's a certain trait which has a probability of 1 in 50,000 happening, let's see what's the probability of, say, 2 or more people actually having that trait. So we've got 50,000 people. We have a probability of 1 in 50,000 of matching the description. Let's work out what's the probability of someone having different number of people matching it. So let's do a simple one. What's the probability that exactly one person matches the description in 50,000 people?
1 in 50,000.
No, it's not.
Perfectly likely.
So,
I'm one of the jury right now. He's guilty. Exactly what.
so let's explain it. Well, in reality, X is the total number of people matching the description.
Stimson did it. Yeah. He's guilty.
So X is the total number of people that matching it. So there could be, in theory, 0, 1, 2, 3, all the way up to 50,000 people matching the description. I suspect the probability that 50,000 match the description is very unlikely.
It could happen.
Mm-hmm.
Oh, yeah, I mean, you could. There's a probability. If it's not 0, it's very, very close to it, though. But you could, but other numbers like 0, 1, 2, 3, you can work out what they are. So, but we want to have a nice formula for it. So the first thing to do is to realise this is a binomial distribution.
You either match it or you don't.
And that's right. So you either match the description or you don't describe. So there's either 2 options. But 2 options are the key thing. So for a binomial, you need to know 2 things. You need to know the number of trials. You need to know what n is. What do you reckon n is in this case? How many different things are we looking at?
What, 3?
More than 3.
Probably 4.
A lot more than 4. Well, essentially we're looking at 50,000 people. That's the number of trials we're doing. For each person you're looking at, what's the probability that a single person you look at matches the description? That would work.
50,000.
That's the probability of success for one trial, so to speak. So the probability of if you pick one person at random, the probability that they match the description is not very likely. But we want to know what the total is among all the whole population. So the probability x equals 1 would be 50,000 choose 1. times by the probability of success to the power of 1 times by 1 minus probability of success to the number of 50,000 minus 1.
Oh my goodness. Okay.
Well, can you calculate?
The power of
Can you calculate to handle it?
49, 29. What is C? Yeah.
What's the answer?
I got 0.367.
3, 6,
Or 0.368 if you want to round. Doesn't matter.
2.368.
Okay, so the formula I'm using is it's NCX PDX 1 minus PDN minus X. That's just the formula I'm using. I just plug in the N's and X's and the P's I've got. Now it's really big. For people who know calculus, that's essentially equal to e to the power of minus 1. That's what it comes down to. So, who's seen E's before?
Love them.
They're in the alphabet.
So it's a mathematical constant your calculator knows. So
We used it in 105, so.
Exponentially.
So it's E stands for exponential or Euler, maybe.
Euler.
Euler is how I pronounce it. E-U-L-E-R. Yep.
That's Euler, but you know, you're allowed to be wrong.
I don't know.
David.
He didn't speak English.
So brutal.
So the way he pronounced his name is probably not how honestly you pronounce it either.
But we do.
So yeah, it may be named after him. So that's the value. So it's about a 37% chance thereabouts of exactly one person matching the description. You can see it's not 100%. That's the main thing to notice. That there's this definite probability that you might get more or less people satisfying it. What's the probability of getting nobody matching the description?
The rest of that.
No. So it'd be 50,000, choose 0, times by 1 over 50,000 to the power of 0, times by 1 minus 50,000 to the power of 50,000.
It'll be like 0.99999 something like that.
Oh, it can't be 9. So we already got 36% for one, so it can't be 99%. It's going to be so the most it can be 64% with everyone else left. And the answer is, I think the same, isn't it, from memory?
Wow.
Check it out.
Yeah, because 1 on 50,000 is like pretty much, it's very small.
Pretty much 0, so it's like 1 times.
Yeah.
Very, very, very small.
So the probability of getting no people or one person satisfying criteria ends up being almost the same. So if they deal with 3 decimal places, actually it's pretty much the same value. So you can see there's about 36% chance each. So the reason what I really want to do is what's the probability that we have at least 2 people matching the description? So Mr. Collins and someone else, essentially.
Mrs. Collins. Got them both.
Well, Mrs. Collins wouldn't match it because it's a male Negro with a beard and a moustache.
Yeah.
So what's the probability of having at least
Collins
2...
Jr. We got him.
At least 2 people matching the description. So what's the chance of Mr. Collins and someone else, and the real guilty person matching the description, essentially?
Psycho.
How would you work out the probability of having at least 2 people?
Thomas Bates' mom. He's like sitting there. He's like, she's guilty. She's dead, but she's guilty.
So, a direct way of doing it, but use 2, not 3, would be I can either get 2 people, or 3 people, or 4 people,
That's it.
or
10 people.
or 50,000 people. So they're all the different options to get
They're all guilty.
at least 2 people. There's lots of things, and the formula we have only works on a single number at a time. You can't sum them all up. So that's a lot of calculations to do.
The only person who's guilty is the judge.
Now, if you keep doing that, the probability does shrink quickly, and you will get to a point in time you go, I think I can say the rest are zeros. But it does take, that seems like a long way. That's the direct approach. Maybe we need to try to do an indirect approach to cover it off. What would be an indirect way of doing it? So try to think opposites. Let's try and think the opposite. What's the opposite of x is greater or equal to 2?
That's less than 2.
So x is less than 2. And how do you do with probabilities when you've got opposite events? What's the formula for it? So if you've got probability of A is 1 minus probability of the opposite event. That's the general rule. So it's going to be 1. So the probability x is greater or equal to is 1 minus the probability x is less than 1. So that's one of the things I mentioned last week. I mentioned lots of things probably. It's really critical here. So that's the result I'm using. So what ways can you get less than 2? What numbers are less than 2?
Well, 0 and 1.
Yeah. So it can either be 0 or it can be 1. Now we worked these out already. So it was 3, 6, 7. And if you type that in your calculator, you'll get the answer. So about 25%. I'm not really rounding very well, but you can give me more accurate than me. So the probability that there is at least 2 people out there, Mr. Collins, who clear mass description, and some other person, maybe the guilty person, for
Mr.
example.
Collins Jr.
There's about a 25% chance of happening. So you have to convict people beyond reasonable doubt, if you know about court laws. That's a doubt. So that would give me some doubt that there's other people out there that might also match the description. So if it's a really small number, then that might be beyond reasonable doubt, I guess. Think that way. Is that a beyond reasonable doubt figure?
Beyond unreasonable doubt.
So I think that it means that it's common enough. So 1 out of 4 times you could get 2 people matching the same description, even a really rather rare description like that.
Both guilty.
And so therefore, just because someone matches the same sort of description, even a rare one, does not automatically make them guilty, because it's a very fair chance that that might happen for twice in the whole pot area. And so this was one of the reasons why the appeal was upheld, and the appeal overturned the original conviction and we dismissed. So this is an example of binomial probability. So binomial probabilities is a way of handling probabilities when you're trying to do with lots of events. You know, probably an individual one, but you want to see how it appeals to the whole thing in one big go. And you can see that this allows you to work out probabilities without having to work out every single value in between. There's just a formula to do every single case for you. And binomial as well is common enough that it's hard coded into Excel and I'm sure into lots of other software programming as well. For your assessment, you have to do it using a little calculator if you ever need to, but it isn't that bad. So that's a more extreme case. So while we have a break for 5 minutes, and we'll do the next. So the next special case is the Poisson distribution. Now, I don't know how to pronounce the name properly, as we were discussing earlier. It's a common French word. Does anyone know enough French to know what it means?
Fish.
Yeah.
What's it? Oh.
It means fish.
Therefore, you're cultured.
Yeah.
So it's named after not a fish, but named after a man who worked for Napoleon. So
Fishes were smart.
he developed this distribution when modelling a number of French cavalry officers who were killed by their own horse. That's where it came from. So another morbid topic, but that was his choice, not mine. So it's basically, it happens when you've got an event which doesn't happen very often, and the occurrence of it happening or not is independent. And as the average number of occurrences is fixed. And so the carry officers, that doesn't happen very often, but there was a fixed average, and the one person dying is independent of another. These are some other examples, or sort of examples. The key assumption with both binomial and Poisson is this idea of independence. So if there is independence of events, each of these would have that sort of Poisson distribution. So first one, if you're at a call centre, you receive on average 20 calls an hour, and the number of calls you receive in an hour will have a Poisson distribution.
That's not a very active call centre, not going to lie.
You'll see why I picked 20 in a second.
There's just a lot of sales, and they just got to be on the phone for a while.
Well, then why the hell do they only have...
So have you been to tech support on like Telstra or something? They take forever.
Yeah, I actually have been on tech support and Telstra for like an hour and a half.
So why I picked 20 you'll see in a second. If you pick big numbers, the calculations get a bit more annoying, but we'll get there. So you can pick so it's roughly counting things over a continuous space or something like that. So continuous time interval. The second one is counting number of trees in a given area. The third one is the same thing. What's the difference between the two forest examples there?
One's 100 square metres and one's 1 square metre.
So a key thing you need to know for Poisson is you need to know the one parameter. That's the average value. So what would be the average value you'd expect for the call centre example? So on average, how many would you expect? What's the average value for X you get? You expect to have 20. 20 an hour. So, because it tells you that. What about the second one, the forest example? What's the average value for Y?
0.08.
0.08. What's the average value for the third one?
0.0008. It's 100 square metres, right?
So it's not the same.
No, because you multiply it by 100 then, so it'd be 8.
It'd be 8.
Oh, yes.
More.
So if there's an average of 0.08 trees per square metre, per 100 square metres, you expect 100 times that.
Yeah.
So you expect 8 trees on average.
I'm silly.
And the last one, so you've got a database server.
I still love you.
You receive 5 requests a minute. Let W be the number of requests an hour. What would be the average value for W?
300.
So 300. So 60 times by 5. So a key thing for all of these is to realise you're looking at something that doesn't happen that often, like it's relatively rare. So it doesn't happen every single instant. That's the idea. And if a request comes in, one request, another request are independent of each other. That's the key idea. Is that independent assumption really valid in all those 4 cases, you reckon? Do that make sense? It's plausible. So you're at a call centre. If one person calls up and another person calls up, are they going to be independent of each other?
Most likely.
The trees. You've got 1 square metre. If one tree's there, it's whether another tree's there or not, is independent of the first one.
It depends on the tree. Because sometimes trees let out like these little thingies that other trees run over.
So that one doesn't sound very independent to me. Like if you've got a big tree even, if you've got a big tree, there's just not physically enough room to put a second one on the square metre maybe.
What if it takes up like 4 square metres for one tree?
That's right. And so that second example probably would fail the independence test. Because once you've got one tree and a block of square metre, it's a lot less likely to have a second one, or certainly a third or fourth, etc. There's a strong dependency there. But when you start looking over a bigger area, like 100 square metres, that interference effect would probably diminish. And so the independence is more plausible, at least for the third case. That might be still a little more. And the last one, again, access request to a database server. If they're coming from all different places, then again, independence seems okay. So if they're not independent, then you really can't use Poisson, you have to do something else. So the key idea of Poisson is you need to look at the values it can take. So it can be number of... so it's number of values. It can either be 0, 1, 2, 3, etc. The key formula you need to know is this one in the middle here. So this is the formula here. And what's the E again? It's a button in your calculator, is really the answer.
Well, you just click it on your calculator. You don't need to know what it is.
So it's 2.7 or like, so a little bit under 3. Your calculator knows how to deal with it. This is really what it comes down to. Lambda to the power of x. What's the exclamation mark again at the bottom?
Factorial.
So factorial. So it's x factorial. So that is the direct formula for it.
That's crazy.
That works fine. If you start plugging in really big values for x, like say things like 70 or up, your calculator can't handle it. It really just fails. And so for large x, you can use an approximation, and one at the bottom there's an approximation for it. For large x, it works really well. So if your x is bigger than 70, it give you the right answer to the number of decimal places that would ever be concerned with. So it's using Stirling's approximation to the factorial. So you can see that the two most fundamental constants of mathematics, so the fundamental constants of mathematics are 0 and 1. They're the two most fundamental. The next two would be E and pi. You can see both of them cropping up in that second formula there.
Oh my goodness, Jesus. There's just no numbers anymore, is there?
There's a 2 there.
Oh, there is.
Oh, beautiful.
Pi is a number.
Pi is not a number.
Yeah, it is. It's a transcendental number, but it's a number.
Does that look like it? Is that in the number line?
There's
Pi.
the same number than me.
If you write down all the numbers in the world, we write that pi
Because
symbol.
1, 2, pi, 4, 3.
I'll let you write them down. So again, those two formulas are helpful to actually calculate. So we'll use the first one whenever we can. You'd only use the second one if you are forced to.
He told the gunpoint, he says use the second.
Well, if you try the first one and your calculator says I can't do it, it's too big or something like that, that's when you have to resort to the second one.
Oh God, let's hope. Can you not put a question like that in the exam? I really just don't want to deal with that.
Have people written down those formulas? Yeah, sure. That's what you need, so make sure you get them down. So again, once you know the formulas, then we can, if you recognise something with that distribution, then we can just pull the formula out and use it when we need to, really. And again, I don't expect you to remember it. I expect you to pull it up from a piece of paper and use it when you need to, I guess. Okay. So this is the course out, and I picked 20 because it's a nice small number. So we got this call centre and receive 20 calls an hour. What's the probability they'll get 19 calls? So I'll let X be the number of calls in an hour. Then X is a random variable and it has a well-known distribution. It's a Poisson distribution. And the average, which I normally use as lambda, it's the traditional letter for the average of this variable distribution. What's the average? 20.
X is Poisson.
So we want to know what's the probability that we have X is
20. If X is the number of calls.
what's the probability that the number of calls we receive in the hour is equal to what? 19. So the general formula, which we want to plug in, is it's e to the power of minus lambda to the power of x over x factorial. That's the general formula.
Filthy.
To apply it. So it's e to the power of minus lambda. What's lambda again? 20. So either minus 20 times by 20 to the power of 19 all over 19 factorial.
That's going to be a big number.
So e to the minus 20 is a really small number. 20 to the power of 19 is huge.
It's not going to be that big.
19 factorial is pretty big too.
Yeah, it's going to take a while to the calculator and do its thing.
And again, you have to use your calculator
Did it in my head.
There you go. Oh my god, 1.08 times 10 to the 10 to the 16. Oh my god. This is divided. Oh wow, that's a decent one.
What is that number?
0.08.
0.08 was someone's suggestion.
Well, if we rounded properly, it'd be 0.09.
Yeah. You know, I'm really lazy. Places will cost for free.
Yeah, I know, that is 2 decimal places.
So that's what Excel tells me.
Yeah. Excel is correct.
Oh, it rounds too. It's just still a 5 decimal place approximation. Excel is good if you can type it in. You can tell it what to do properly. That's a challenge. So everyone okay? Everyone can work out the buttons in your calculator. If you don't, just ask. That's fine. So we've done factorials and powers, but we haven't done the exponentials. So the exponentials is really the E bit is probably a shift ln button on your calculator. It's probably a hand to type it in your calculator.
Shift log E.
And ln stands for natural logarithm, which is log base E.
Oh, is that what it stands for? Logarithm. Oh wow. I just thought people like they're just really lazy. They don't have 3 letters, so it's like kind of like you have the form.
So everyone could use your calculator to get that answer. If not, can't see at the end. That's okay. So let's do the database. So for a database server, you've got 5 requests a minute. What's the probability the database will receive 310 requests in 1 hour? So I would let Y be it's supposed to be Y, the number of requests in an hour.
I'm disappointed.
So Y is this Poisson distribution. We need to know the average so we can do anything with it. What's the average number of requests we get in an hour?
300.
So it's, as you said, 60 minutes times by 5 requests a minute gives an average of 300. And if you don't put 300 there, I mean, you have a very different answer. So you want to know the probability that the number of requests is equal to 310. And so at first glance, it'd be the same form we had before, so e to the minus lambda to the power of x on x factorial, which would be e to the minus 300 to the power of 310 over 310 factorial. If you get your calculator,
it is going to be.
if you try your calculator, you'll fail. I don't know where at point in time, but certainly on the bottom, the 310 factorial it just won't handle. I suspect it might fail before that point.
Yeah, the top one is too long.
So
Excel do it.
But
yeah.
It's all your RAMs.
Excel has no difficulty at all doing it.
Cool.
Maybe on one of the the uni computers, but
It won't do it. It doesn't use the formula directly. It uses some other tricks, essentially. So one of these tricks is to use that large, the approximation, which was e to the x minus lambda on x to the power of x over square root of 2 pi x, if I remember correctly.
That's it.
Can I just not do that question? That's way too long of a formula. If I see that in an exam like that.
You can. I don't know if I'm that.
And so in this case, that'd be e to the power of x minus. So x is 310 minus 300.
Which is just it's easy.
Lambda is 300 over 310 to the power of 310 all over 2 pi times by 310. So that would be the days. And that's not so scary for your calculator, partly because e to the 300 minus 310 is just 10. So e to the 10 is not nearly as extreme a value as e to the minus 300. And that's 30 over 31 power of 310 over whatever the bottom is. So some of those really big and small values aren't present so much anymore, and so calculator can handle it. What answer you get?
On the bottom, is that 2 lambda?
2 times by pi.
Ah, 2 pi.
So 2 pi times by the x value, so 310 in this case.
That's right or wrong?
So it's so in Excel it's
Can I just use Excel for these?
no. So it's x equals Poisson distribution. We want 310 with an average of 300, and you just type in false at the end for some reason. And so
That's what I got.
so about 2%.
Easy peasy.
So, I mean, I wouldn't normally give an example, but you can, like that, but you can see that if you just pick random examples, you can get ones that are quite big, and there is more mathematics to help you do with those sort of things. And so whoever programs this formula for Excel has programmed some of those tricks in just so the numbers don't blow out, essentially. So just summarising the Poisson distribution, the average and the variance of the Poisson distribution are both equal to this parameter lambda. So lambda is the average, that's sort of how we solve it, that's how you describe it, but it happens to also equal to the variance. And so why would you ever use it? So if you're ever trying to do simulations where you've got a web page, number of people coming to a web page or accessing a database, or call center, lots of those sort of things. Poisson distributions are common because we expect people to turn up to these things in an independent fashion. And the time between people coming is given by another distribution called the exponential. So these are common things you might want to do when you're doing various simulation exercises, for example. So they also crop up in physics if you do that sort of stuff, as in the number of radioactive atoms that would decay in a given minute would have a Poisson distribution. So it crops up often. Okay, so last thing I want to consider is when we have a bivariate probability distribution.
What's that bit rate?
So bivariate is just a very fancy way of saying two variables. So you've got two variables at the same time. And a common way of doing that is just to have a nice two-way table, like you can see on the slide there. So in this case, I've got two variables. One of them is the x variable, which is the 1, 2, 3 going across, and the other one is y, which has values -1, 0, and 1. And so these are all the probabilities of these various things happening. So the lines indicate the totals. So this last column and the bottom row here are the total probabilities of the various things. So let's just copy it.
Cut it off.
I can't feel it, David.
That's good for cutting it off.
So you can't get one with your evil legs.
So from that table, so x is going across, y is going down. What's the probability that x is 2 and y is 0? What's the probability that both of them happen at the same time? Any ideas?
Whatever that 0.1 thing is. 0.1 thing.
So if you go x equals 2 and y equals 0, the number that matches both of them would be the 0.1. So it's really just reading off the table. So it's the value in the table that matches both of them.
That's way too hard.
It gets harder. So giving a name, this is called a joint probability. So it's a probability of both of them having the same time. So it's really just in this section. Essentially.
20. Probability.
What's the probability that x equals 2?
0.2 plus 0.1 plus 0.1.
Okay, so one way of doing it, x equals 2 can either be, you can either be the 0.2 or the 0.1 or the 0.1. So they're the three options you can have.
So it's just a 0.4 there.
And if you add them all up, which has been done for you in this table here, you get the value from the margin. So the 0.4 below just tells you what the probability of x equals 2 is. Again, so that's called a marginal probability.
That's solid.
Let's spell it properly.
Change Caitlin's Facebook thing in a relationship with him.
I think
When Ben changed
Oh, yeah.
Caitlin's Facebook status to a relationship with him.
people like, oh man, it was like, well,
Okay, let's just do this last one. Like what it says. What's the probability that y is 0 if you know that x equals 2? So, putting it away, what's probably y equals 0 given x equals 2? That's how you read it directly. So the vertical line you read is given. You might want to say otherwise is what, when x equals 2, what proportion of time do you get y equals 0? That's the English way of saying it.
1.
So let's just scrub out some more stuff here. So given x equals 2 means we know that we're in that column. We're automatically in that column. So what given in that column, we want to work at the probability of getting y equals 0. So the way you work at general probabilities in general, we have to apply here, is the number of ways of getting the particular event we want. So there's going to be a 0.1 chance of getting y equals 0, but we have to divide by the total number of ways that we might want to consider it. So how many different ways are there of getting in that column all up?
3.
Well, it's the number down the bottom.
Oh.
So the probability of being in that column is 0.4.
Oh.
So number of ways of getting the particular case is 0.1 out of the 0.5, all the different ways of getting in that column all up, which gives you a quarter or 25%. Now that's doing it without formulas. If you like formulas,
I love them.
the probability of A given B
Does this one have numbers in it?
is a probability of A and B divided by the probability of B.
Nope. I'm done.
So no numbers. So that's the general sort of formula that you do for conditional probabilities. So in that case, the probability of y equals 0 given x equals 2 would therefore be equal to probability of y equals 0 and x equals 2 divided by probability x equals 2. That's how you would do it. And they are the numbers that we wrote a second ago, essentially. That's the 0.1 over the 0.4. Gives you exactly the same number as before. So you can do it a little bit more intuitively by just thinking it's number of ways of getting the event divided by the total number of ways we want to consider, or you can use formulas, either or. And that last one's called a conditional probability, like we've used the same name before, as a matter of fact. Joint, marginal, and conditional probabilities. So other things you might want to do with this, and we'll do that tomorrow, is what's the expected value of x? Or the average value of x? What's the average value of y? And what's the average value of x given y equals 0? So you might want to work an expected value on some condition. So we want to do all those different options. The basic way of doing that is just work at the probabilities and do the same trick we did at the beginning of today's lecture by just basically summing the x value times by some sort of probability and adding them all up. That's a basic idea. But we'll see more of that tomorrow. So in recap, we've just been dealing more with probability distributions. So looked at two special cases, binomial and Poisson, and looked at how to work out expected values or / averages and standard deviations is the main thing we looked at. So I'll see you guys tomorrow. Just not the probability.
You are currently the only participant in the conference.